Steve the prehistoric sheep herder has a problem. Each morning, he lets his sheep roam free in order to graze. However, he seems to always have less sheep at the end of the day than at the beginning. So, Steve decides to keep track of how many sheep he has by using stones. For each sheep that leaves his cave, he places one stone into his bag. When the sheep return later in the evening, he removes the stones one at a time as the sheep enter. If he has more stones than sheep, then he knows that he needs to go out looking for the missing ones. We say that two sets are equal in number if you can find a bijection between the two. For example, the set of 1, 2, 3 is the same size as the set A, B, C because I can pair 1 with A, 2 with B, and 3 with C. Now, what if Steve has an infinite number of sheep? Can we still count how many sheep he has? It turns out that we can. We just pair each sheep with one natural number. This shows that there are exactly as many sheep as there are natural numbers. We call this type of infinity countable infinity. We call it countable because we can go down the line of sheep and assign each one a natural number. If we keep doing this to infinity, we haven't skipped any sheep and we haven't skipped any natural numbers. Formally, a set is considered countably infinite if we can biject that set with the natural numbers. In other words, a set is countable if we can list it out. We've looked at the natural numbers, but what about the integers? Are they countable? Can we list them out? Another way of asking this question is, can we assign an integer to each sheep and eventually cover all of the integers? We can. Start with 0 for the first sheep, then 1, then -1, then 2, then -2, and keep the process going forever. We aren't skipping any integers, and we can do this forever, so we've shown that the integers are countable too. One surprising result is the fact that the rationals are countable. We know that the rationals is the set of all the numbers that can be expressed as an integer over an integer. There seems to be a lot more rationals than integers, but we can pretty easily show that we can count the rationals in the same way. We construct a table as follows. In each row, make the numerator the number of that row minus 1. Then make the denominator of each column the number of that column. So, we've created a table of every possible rational number. We have a few repeats, like 1/2 and 2/4, but that's fine to overcount. Overcounting is okay because we can just go back later and eliminate all the repeats, and our numbers will still be in a list. We start counting by starting at the top left and following the numbers in a pattern like this. If we keep going, we've included every rational number on our list. So we can biject the rationals to the natural numbers. So there are just as many rationals as there are naturals. We've seen that the naturals, the integers, and the rationals are countable. But can we go further? Are the reals countable too? Recall that the real numbers are both the rational and irrational numbers. So they're pretty much any number that you can think of. Pi, -2.38, 4, 10/3, e, and every combination of those is real too. Now, Georg Cantor, a 19th century German mathematician, managed to prove the fact that the real numbers can never be put into a bijection with the natural numbers. This fact would prove that the reals are not countable and that they can never be put into a list. He proved that we cannot put the real numbers between 0 and 1 in a list. If the reals between 0 and 1 are not countable, then all of the reals cannot be countable. Let's take a look at what Cantor proved. First, we assume the opposite of what we want to prove. We'll see later why this is helpful to assume the opposite. So, we assume that the real numbers are countable, or that they can be put into some list. Let's do that. I'm using the letter D for digit, where the first subscript denotes the row, and the second denotes the column. So, D23 would be the third digit of the second number. Now, let's make a new real number. Let's call it A. Let's look at D11. If it is 5, then the first digit of A will be 6. If it is not 5, then the first digit of A will be 5. All we're trying to ensure is that A cannot be equal to D1 because their first digits are different. Similarly, we use D22 to find the second digit of A. Since D22 is not 5, the second digit of A becomes 5. Once again, since D33 is 5, the third digit of A is 6. We continue this process of creating this new number A. This proof is known as Cantor's diagonalization argument because it can utilize the diagonal in creating A. Now, let's compare A to our first number in the list. They are not equal because they differ in the first digit. Similarly, A is not equal to our second number because they differ in the second digit. We can pretty easily see that A is not equal to any of the numbers in our list because they always differ by at least one digit. But wait, we just made our list so that it consists of every real number, and A is a real number, so A must be on the list. but we just showed that it cannot be on our list. How can A be both on and off the list? This is where we get our contradiction. Now, let's look back at what we initially assumed. We assumed that the real numbers can be put into a list, and we've shown that this must give a contradiction. So we're forced to conclude that our initial assumption must have been wrong, and that the real numbers cannot be put into a list. So we see that even though both the natural numbers and the real numbers are infinite, they are different types of infinity. The naturals are countable because we list them out, but the reals are even more infinite than the naturals because we can't even put them in a list. Can we go bigger? If the real numbers are all the points on a line, then what about all the points in a plane? Or all the points in 3D space? Or in a 100-dimensional space? The result turns out to be pretty surprising. Let's take a look at the points in the plane first. Remember that two sets have the same size if we can find a bijection between the two. Like we did with Cantor's proof, we're just going to look at all the real numbers between 0 and 1 and all the points in the plane with x and y coordinates between 0 and 1. Let's take a point on the number line and call it x. We'll name the digits d, where the subscript corresponds to its place in x. Now we create a new point in the plane called a. Let's say a has x coordinate 0.d1, d3, d5, d7, and so on. Let's also say that a has y coordinate 0.d2, d4, d6, d8, and so on. So we split up x into two new numbers, and we can associate these two new numbers with coordinates in the plane. Similarly, for each point in the plane, we can mesh its coordinates together to form a new number on the number line. So we've managed to associate each real number with a unique point in the plane. This argument can be quite easily extended to include every other point on the real number line and every other point in the plane. So, since we've bijected between the real numbers and the points in the plane, we've managed to show that there are exactly as many points on a line as there are in the plane. Quite surprising result when you think about it. In fact, we can do a similar process for three-dimensional space. We just take each real number on the real number line, and instead of splitting it up into two numbers, we split it up into three numbers. This argument can be extended to any dimension in Euclidean space. So, we've managed to answer our original question, and yes, a 100-dimensional space has exactly as many points as a number line. These sorts of fascinating results appear to be paradoxical. How can there be as many points on the real number line as there are in the plane, when the plane is just a bunch of lines? These sorts of questions were the exact kind that some earlier mathematicians questioned Cantor over. One mathematician at the time, Henri Poincaré, even said that Cantor's ideas are a grave disease of mathematics. Some scholars even regarded Cantor's proof as an affront against the infinity of their God. These results, while counterintuitive, have stood the test of rigor of mathematics. Today's mathematicians now regard Cantor as one of the greatest thinkers to completely challenge and dispute the popular opinion about a topic. So, the next time you count sheep in your sleep, remember how far that simple idea of counting can get you. Thanks so much for watching. I'd like to give a huge thank you to all those behind the Breakthrough Prize, especially those who encourage so many young scientists and mathematicians in their pursuit of knowledge. I'd also like to thank Sal Khan for his inspiration and dedication to the advancement of their understanding. Thank you.